we will explain a method for constraint optimization that relies on quadratic approximations of the objective function and the constraints. So here is the problem formulation considered. We want to find the design variables x to minimize the objective function capital F of x so that the constraints are satisfied. Note that we consider a single objective function and only equality constraints. So the method of approach is to write the Kuhn-Tucker equations and the Kuhn-Tucker conditions, and solve them using Newton's method. So the Kuhn-Tucker conditions dictate that the gradient of the Lagrangian should be equal to 0 at the optimum values of the objective function and the Lagrange multipliers. So this is the Lagrangian, the function that we want to optimize. And the key idea is to solve this equation using a first order approximation of the Lagrangian. So this is a sequential method where we have a linear approximation of the Lagrangian, and we solve this equation. And we start from initial guesses of the design variables. These are called x0, and also initial guesses of the Lagrange multipliers. And we solve a linear equation for x and lambda. Okay, so this is the expression for the gradient of the Lagrangian, which is obtained as a linear approximation of the gradient of the Lagrangian at the initial point, and the gradient, the Hessian of the Lagrangian times the increments of the design variables and the Lagrange multiplier. So we try to find now a linear approximation that the gradient of the Lagrangian must be 0. So we have this equation. Let's look at the matrix. This is the Hessian matrix of the Lagrangian. We have the constraints, the matrix of the constraints, and here are the increments by which we want to update the design variables and the Lagrange multipliers. And this is the right hand side, which is a vector. We have an upper part that is the gradient of the Lagrangian, and the other part is just the equality constraints. And the negative sign is before this the left hand side. So we solve this equation and we determine the increments by which we want to change the design variables and the Lagrange multipliers. So we solve for delta x and delta lambda. And once we have these increments, then we update the estimates of the design variables and the Lagrange multipliers at the optimum using this equation. We simply add to the previous estimate of the design variables and the Lagrange multipliers, the increments that were obtained by solving the above linear equation. And we continue this process until we have obtained convergence. Here is an example optimization problem. This problem involves two design variables, x1 and x2, and we wish to minimize the objective function capital F, which is the first design variable times the square of the second. And we have a constraint denoted by h of x1 and x2, and this constraint dictates that the points x1 and x2 are on a circle that is centered about the origin, and the square of the radius is equal to 2. So this is the Lagrangian function consisting of the objective function plus the Lagrange multiplier times the constraint. So this is the expression. The first term is the objective function. The second term is the Lagrange multiplier times the constraint. In order to find a linear approximation, we find the gradient. Here is the gradient. These are the derivatives of the function with respect to x1 and x2. And this is the second derivative. And this is a matrix, the Hessian matrix, with 4 terms. These are the derivatives of the constraints. So now we formulate the equation that we can use to update the estimates of the design variables and the Lagrange multipliers. This is the equation. We have a 3 by 3 matrix. These are the increments that by which we want to change the estimates of the solution and the constraints, and this is the right-hand side. This process, if it is repeated several times, maybe about 10 times, it converges to the optimum at which the first design variable is minus 0.816 and the second design variable is minus 1.155. So now let's run a program to solve this problem. This is a MathCAD program. So we define the objective function. This is the equation for the objective function. It's x1 times x2 squared. And we have the equality constraint, which is that the sum of the square of the first term and the square of the second minus 2 ought to be equal to 0. Here is a plot of the objective function, and we have isoquants of the objective function, and these are the isoquants of the objective function, these curves, and the constraints. Now, in order for the constraint to be satisfied, all the designs, candidate designs that satisfy the constraint, that is, the feasible designs, lie on a circle centered at this point, 0, 0, and it has a radius. Well, the radius is, the square of the radius is 2. So the radius is square root of 2. And this is a composite function that we will try to minimize. So this is an initial guess. The first design variable is minus 1.5, the second is minus 1.6, and the Lagrange multiplier, the initial guess is 0. Now, I'm going to spoil, this is a spoiler, the true solution is minus 0.1, 0.817, and 1.155. And I'm showing that to show how far away our guess is from the true solution, which is minus 0.817 and minus 1.155. And this is the distance from the solution, from the true solution. So now let's pretend that we don't know the solution, you didn't hear it from me, and we solve the optimization problem. This is the first iteration. We form a linear equation. So these are the terms on the left-hand side, and this is the right-hand side. We solve this, and if we solve it, we find that x1 is minus 0.1, minus 0.822, and x2 is minus 1.35, and this is lambda. And we can find the distance from the solution. So the true solution is minus 816 and minus 1.157. Okay? So our estimate for x1 is pretty close. The estimate for x2, though, is not good enough. So let's make a second iteration and see if the error, which right now is about 20%, will drop. This is the second iteration. We update the matrix A in the left-hand side of the equation, and we update also the right-hand side, and here is the solution. So the first variable now is the estimate of the solution is minus 0.828. And the second variable, the value is minus 1.163. And this is the Lagrange multiplier. Now, this should be compared to these values that represent the true solution. And as you can see, our solution is quite good, quite close to the true solution, and the distance is just 0.014, which is pretty good. So we presented a method that can perform constrained optimization of one objective function, and the method relies on the Kuhn-Tucker conditions to update the design variables until it finds the optimum solution.